check. Hello, hello, check, check.
Yeah. Hello. Hello. Am I audible?
Dear students, please settle down. Everybody come forward now. This is getting recorded, so you have to come forward. Come. All last bench. Start from there. Everyone. Sir, are you able to hear us? అది important. उसका sound check करो उनका. All of the information online. अभी हो गया तेरा channel. Sound वाले रहा. Sir, we can't hear you. Yes, sir.
Okay. So yeah, I think now it works. So should I start or
I'll
anything
just give a
else?
brief introduction, sir, then you can start. Am I audible, sir? Fine, students. So we'll start our second session. He is Dr. Brijesh Kumbhani. He is from IIT Ropar. Actually, his flight tickets were booked. He was about to come because of the floods in Himachal Pradesh and Punjab, right? He couldn't catch his flight at the airport. So we have an online session now. So he received his PhD degree from department, yes. We did not clap, just listen to the introduction of him. Dr. Brijesh received his PhD degree from IIT Guwahati in 2015. His research areas include MIMO, wireless communication systems, and UWB systems. Current research interest lies in the domains of energy efficient wireless technologies with high spectral efficiency, and he is into the two-user cooperative transmission schemes. So now his talk is concentrating on this. So I request Brijesh sir, if I am audible, to start his session. Am I audible, sir? Yes, sir.
Yes, yes,
Yes,
yes.
yes.
So yeah, fine. I will start. Hmm? Okay. So let me share the screen. Okay. So I hope my screen is visible. Okay. So let me thank the organizers for giving this opportunity, and I'm very sorry that I could not come there personally, even though I was all prepared, but due to heavy rains, the way to airport were blocked, and I could not travel. So I had to give this talk virtually, and the topic would be review of wireless communications and MIMO techniques, right? So in this talk, what we will discuss is a little outline, that is why MIMO, that is multiple input, multiple output. So it is all in respect to systems, right? So why MIMO? It also includes the demands from wireless communication systems that we need, right? So it is the technology evolution, how the communication systems, especially for wireless communications, evolved from binary or digital systems, analog systems, to higher order modulation schemes, and then diversity schemes, and then comes the MIMO, and then some variants of MIMO systems, and then we will see how what are the advanced MIMO systems and what all are there in being used in 4G or 5G, right? So this is okay. Yeah, it is the advancement of wireless technology, where we started with analog modulation schemes, which were amplitude modulation, frequency modulation, phase modulation, and quadrature amplitude modulation, right? Wherein in digital modulation schemes, what we call is phase shift keying, frequency shift keying, amplitude shift keying, and QAM, that is again quadrature amplitude modulation, right? So in the primary difference between analog communications and digital communications is that the message is in digital form when we consider digital modulation schemes or digital communication systems. Okay, while in analog communication systems, the message is in the form of analog signal, right? So the directly uh, we can just convert any signal into electrical form, amplify it, and modulate. That will be analog modulation scheme. While in digital modulation schemes or digital communication systems, what we need to do is the natural signals are all analog signals. They are passed through some transducer to convert it into electrical signal. That electrical signal is then in the form of voltage or current. It needs to be amplified, and amplified signal is then further digitized, right? So the process of converting analog signal to digital signal, right? That is followed, right? That is sampling, quantization, and then encoding, right? So that it comes into digital form, and then digital modulation schemes can be applied, right? So we will not be discussing about why all the systems are being digitized nowadays, right? But there are advantages, like we can use multiple access schemes, we can use diversity schemes, and the topic of today's talk, the MIMO systems, right? So MIMO systems are also possible only if we have digital messages, right? So if we have analog messages, then analog communication systems, we cannot use many of these techniques available. Okay, so this is when we talk in the perspectives of communication systems, right? Otherwise, the digital systems have many other advantages. Okay, so multiple access schemes is to accommodate many users, right? So how we can accommodate many users within the constraint of available resources, right? So the commonly known multiple access schemes are TDMA, CDMA, and FDMA, right? So that is time division multiple access, in which the time axis is divided into time slots, and some time slots are allocated to different users, right? And then CDMA is code division multiple access, in which some orthogonal codes are assigned to users so that their signals do not interfere. And then we have frequency division multiple access, in which uh, we make many channels from within a given frequency band, right? Then we use diversity schemes. There, the diversity schemes can be of many types, maybe time diversities, frequency diversity, polarization diversity, or space diversity. Space diversity has got much of popularity because it doesn't require any change at the transmitter side. So the same transmitter designed for single antenna system can be used for the receiver of space diversity, right? So we don't need to change any modality at the transmitter if we want to use space diversity at the receiver, right? While in time diversity, frequency diversity, or polarization diversity, we need to either change the transmission scheme or the antenna designs, right? So that is why space diversity has become a little more popular. Even in case of time and frequency diversity, we need to use extra resources also. So then we will move towards MIMO systems, and then we will discuss various variants of MIMO systems. Okay. Yeah. So then next we have this mobile telephony, right? So in mobile telephony, we have cellular structure, right? So cellular structure is nothing but the whole geographic region is divided into small cells. And probably if you are familiar with the mobile communication systems or wireless communication systems, we have different cells which are conventionally of hexagonal shape, right? But that notion no longer exists. Nowadays, we have heterogeneous cells also, right? And in each cell, we use the notion of frequency reuse, right? So frequency reuse is nothing but once we cross certain distance from one transmitter, the signal from that transmitter do not have sufficient strength to interfere, and then at that location again we can use the same frequency, right? Then from going from one location to other location, we have the notion of handoff, right? So when you cross the boundary of one cell and you move towards the another cell, you need to do handoff, right? And then we had roaming, right? So this roaming was very popular when we had 2G 2G communication systems, right? Second generation, even when we want to move from one state to other state of the country, we don't get coverage, or we don't get a network, right? So that time we had to specifically inform the network operator, right? So that I am planning to go from my state to some other state. Kindly allow me to use the network, and they used to take charge for that, right? So that is what the concept of roaming, right? But nowadays we don't have roaming within the country, right? So these all processes are governed by the Telecom Regulatory Authority of India, that is TRAI, right? It also amends its rules and regulations time to time, and nowadays the notion of roaming is not there when we are traveling within the country, right? So then there are standards, right? So standards are like GSM and CDMA were used in 2G. The frequency bands allowed were 900 megahertz, 1800 megahertz, right? So this GSM was narrowband and CDMA was broadband. Then the TDMA and FDMA was used in GSM, and CDMA technique was used in CDMA, right? So CDMA standard was CDMA 2000, right? So then the modulation scheme that was being used in GSM was GMSK, and the modulation scheme that was used in CDMA was the spread spectrum modulation, right? So these different modulation schemes, right? So we are not going to discuss in detail. Just I will just tell the names only, right? And then from 2G to 3G, the system moved to CDMA, and then again wider than the CDMA that was used in 2G, and that is why it is called WCDMA standard, where it was wideband CDMA, right? So again going from 3G to 4G, right? So we call it as LTE or LTE advanced, right? So LTE is the beginning of 4G, and then when the 4G technology matured, it is LTE, right? And then these technological developments were mainly for the internet services, right? So WCDMA was mainly for the here in 2G it was GPRS, then in 3G we had HSRP scheme, right? So there we in 2G the edge technology was also introduced, right? And then uh, in 4G we had LTE, and in 4G one more facility was there, and that was VoLTE, right? So it is a similar version of the internet telephony, right? So internet telephony was normally named as it was normally named as VoIP, that is voice over IP, right? So that is voice over internet protocol. Now LTE is the technology, and when we say transmit voice over this technology, we say that it is voice over LTE, right? So now from 4G onwards, voice has also been integrated in the internet services of the wireless communication systems, right? So then 5G is under standardization. Still, it has been implemented, but the standards are still being revised time and time, right? So 5G, it is whatever systems are being implemented, right? They are still under testing phase, right? So then, what are the wireless technology requirements, right? So the wireless technology requirements are minimum delay or latency for real-time applications, right? So we don't need any delay in the transmission of the message, right? So for example, when a phone call is going on, right, if there is a huge latency, in that case, when the speaker speaks, after that, after 1 or 2 seconds, the listener will listen, then the listener will speak, after 1 or 2 seconds, the other side some voice will go, right? So that is not good user experience, right? So this latency is not only for user experience, but it is for some real-time applications like in robotics, or when you have remote control of some devices, right? So in that case, latency is very important, right? So from any wireless technology, we need minimum delay or minimum latency, while we need high spectral efficiency, because high spectral efficiency is because we have limited bandwidth, right, over which we transmit our messages, right? So when you have high spectral efficiency, you will use the bandwidth efficiently, right? So within a given unit bandwidth, you will transmit more and more data. That is what high spectral efficiency means, right? So once high spectral efficiency is reached, right, is achieved, then we can achieve high data rates as well as high channel capacity. Right, so data rate and channel capacity and spectral efficiency, they are interrelated. All right. So within a given bandwidth, how much channel capacity you can achieve, and how much data rate you can achieve near to the channel capacity, right? That is the spectral efficiency. Okay. So then there can be different scenarios, right? So different scenarios are noise limited scenarios, interference limited scenarios, and a limited bandwidth, right? So in noise limited scenarios, the solutions may be very simple, right? In noise limited scenarios, you just transmit the signal at higher power, right? So when you increase the signal power for a given noise power, the SNR, that is the signal power to noise power ratio, will increase. And when the signal power to noise power ratio increases, it is definitely the signal conditioning becomes good. When signal conditionings are good, we can achieve higher channel capacity and higher data rates, and we can transmit more data within a given bandwidth, right? So then we have interference limited scenarios in which we cannot transmit high power signals, right? This interference limited scenario is more applicable to the cellular communication systems, right? And most of the wireless communication systems nowadays use the cellular system, and that is why we all have these interference limited scenarios, right? So how we can improve the performance within these scenarios, we will see in the next slide, right? And then we want, what we want is high bandwidth per user, right? So why high bandwidth per user is required? So that is the channel capacity equation. If you remember the channel capacity equation, it is B times bandwidth times log of 1 plus SNR, right? So bandwidth comes into picture there. So if we increase bandwidth, right, of course we are not going to increase it beyond a certain limit, right? Because the channel capacity then will saturate because of the noise power, right? So noise power is also proportional to bandwidth of the channel, right? And that is why we can have high bandwidth per user to improve the data rate up to certain level, right? And that is why there are certain technologies for high bandwidth per user utilization, where single user, single carrier transmission can be possible, or multiple carriers, which is used in OFDM. That is also possible, right? So let us see how we can achieve high data rates, right? So high data rates is in noise limited scenarios. I said that it is very simple in noise limited scenarios that transmitted signal power we can increase, and we can get the improved signal power, right? So further increasing the bandwidth is also one of the solution, but then in increased bandwidth we'll have more noise power, as well as it will make the channel frequency selective, or there will be time dispersion, right? So these two solutions, right, increasing the no, increasing the signal power and increasing the bandwidth, are not very good solutions, because when we increase the signal power, right, the battery drain, right? So that is when we talk about mobile equipment, right, our mobile handsets. If we increase the transmitted signal power, then the devices which are battery operated will consume more energy from the battery, and the battery will drain faster, right? So that is not a good solution. So what can be the other solution, right? So that is reducing distance between transmitter and receiver, right? So transmitter and receiver, if distance reduces, we need lesser signal power to reach the cell boundary, right? So that is what the for every generation we get reduced cell size, small cells, or we have bigger cells, and now the cell density is increasing, which is again giving one more challenge, that interference will also increase, right? Because the cells are coming near and near, but we cannot reduce the power such that the edge user do not get any coverage, right? So here one of the possible solution is we have large number of cells, right? And then we have receive antenna diversity, right? That is also one possible solution, right? And then we can have multiple transmitter antennas to direct more radiation towards the receiver, and more symbols every time by using beamforming as well as multiplexing, right? So then what else is there is advanced RF design to improve the receiver noise figure, right? So when the receiver noise figure improves, we can have better reception, right? So the effect of noise will reduce when we improve the noise figure, okay? So then when we have interference limited scenarios, right? So interference limited scenarios, increasing the signal power doesn't work, because when you have multiple transmitters transmitting at same frequency, if you increase the signal power, that signal will interfere the other users, right? So because of frequency reuse, interference from nearby cells is also a challenge, and because of that, signal power cannot be increased beyond a certain limit. So now again, it is more bandwidth, more interference, and the channel is becoming frequency selective. So we don't either go for increasing the bandwidth also, right? So then again, reduced cell size, receive antenna diversity, multiple transmitter antennas with beamforming and multiplexing, and special processing through smart antenna. That is what there is no reception from the direction of interference, right? So that is what we can do in interference limited scenario, in addition to what we can do in noise limited scenario, right? So reduced cell size, receiver antenna diversity, and multiple transmitter antennas, these are the common solutions in noise limited scenario as well as interference limited scenarios, right? And in limited bandwidth, right? So in limited bandwidth, we cannot use a higher bandwidth. So what we can do is higher order modulation can be done, right? So higher order modulation we can use, and higher order modulation along with channel coding, so that the spectral efficiency we will reduce a little bit, but power efficiency will improve, right? Because channel coding, it enables detection as well as correction of some errors, right? So error correction codes like Hamming codes and all can be used, right? Yeah. So then we have performance degradation for higher order modulation. and this is what we will see, how the degradation in higher order modulation comes when there is same system, right? So then receiver antenna diversity, transmitter antenna diversity, and multiplex transmission, these some of these can be used to take care of the performance degradation, right? Okay, so let us see what would be the effect of diversity, and how diversity can improve the system performance, right? So that we will see step by step. Okay, so this was the general idea of what are our expectations from wireless communication systems, and to achieve those expectations, how can we proceed, right? But there is no single answer, right? See, for example, if we see and if we say that, okay, I want to increase my data rate, but I want to keep the bandwidth same, what should I do, right? So then there are multiple solutions, and those solutions will work in different types of scenarios, right? So there is no universal solution, but the solutions need to be implemented based on the situation, based on the geographical location, based on the user density in that area, and interference levels and such parameters, right? So let us take an example of binary phase shift keying modulation, right? So binary phase shift keying modulation, let us say we represent bit 0 with phase 0 and bit 1 with phase pi, right? Uh, Okay, so when we represent bit zero with phase zero, right? So it is represented like this, right? That is the dot on the right hand side, and one with phase phi is represented as this dot on the left hand side of this figure, right? So mathematical representation is like this, where we have a carrier with frequency fc, right? And that frequency, right, is associated with the phase, right? And that phase is containing the message. Okay, so every time when the message changes, right, so or the message bit changes, the phase of the carrier is changed, right? So we can represent that S0 is represented as A cos 2 pi fct, and S1, that is for 1, it is represented as A cos 2 pi fct plus pi, right? That is minus A cos 2 pi fct. And the constellation diagram is nothing but it is the this signal is represented in the vector form, and that vector form is a vector form signal, right? So it is plotted in two-dimensional, three-dimensional, or whatever is the dimension of the vector, right? So then we get the constellation diagram, right? So this is the constellation diagram for BPSK, which is binary phase shift keying, in which every symbol is uh, every symbol is carrying message of 2 bits, right? And message of 1 bit, right? Because there are only two possibilities, right? So bit 0 is represented, bit 1 is represented. Okay, so we have two vectors which are representing 0 and 1 with magnitudes a minus a. So it is a one-dimensional modulation scheme. So further we have Emery PSK, where this phase part, right? So it was, instead of pi I, now we have 2 pi I by m, right? And m is the order of modulation. Okay, when we simplify this, right? So when we simplify this, what we get is this, right? So the simplification is like this, and the constellation diagram is shown for 8 PSK, which is 8 PSK, right? So M PSK is this M gives the modulation order, right? So modulation order, by this modulation order, we say that how many points are there in the constellation diagram, right? Okay. So now, how the bit error rate depends on this constellation diagram is that the minimum distance between these 2 points, right? These points get displaced when there is noise. Okay, when there is addition of noise, this point will not be at its original location. Okay, so it is, for example, this SIT is given, right, and plus there is some noise, right, and that noise will also be of this kind, right? So that is, in the in this term there will be noise, in this term there will be noise, and because of that noise, this AC will change, AS will change, right? The magnitude will change, and the point, instead of being at its original location, it will be at some different location, right? And the effect of noise is seen over here, right? See the noise, effect of noise on the constellation diagram, right? So I hope different colors are displayed, and the black star, right? So that is where there is the signal when there is no noise. Okay, and then this pink dot, right? So larger dot, pink color, right? That is when the SNR is 30 dB, right? It means the signal is 1,000 times larger in power than noise. Okay, then blue is 20 dB noise, 20 dB SNR. That means the signal is 100 signal power is 100 times larger than the noise power on an average, right? And then when there is the SNR of 10 dB, right? So that is the red ring completely is being shown, right? So it is still, the signal is 10 times larger in power, 10 times larger in strength than the uh, than the noise, right? So when we want to separate them, or when we want to decide which signal was transmitted, or which of these dots was transmitted, right, we need to find some boundary, right? So for example, this boundary is found, right? So for this particular boundary, right, so for example, if we want to find this difference between these two, right, and we find a boundary over here, right, so we can decide between the two, if whether it is on one side of the boundary or the other side of the boundary, right? So this is just showing that as you increase noise, right, or you reduce SNR, the spread of the constellation points is more and more, right? So it is no noise, then 30 dB SNR is pink, then 20 dB SNR is blue, and then 10 dB SNR is red, right? So 10 dB SNR, we cannot distinguish different constellation points also. It becomes a type of ring, right? So even if you go towards 5 dB SNR, right, so then it will be even more difficult to differentiate between two symbols. Okay. So now, constellation, what happens to the constellation with higher order modulation scheme, right? So let us see an example of quadrature amplitude modulation scheme, right? So quadrature amplitude modulation scheme and its constellation diagram is shown over here. We have shown two constellation diagrams. One is for 4 QAM, and the other one is for 16 QAM. Right, so in 4 QAM, if you see, the average energy for every symbol, is 2. Okay, so energy carried by this symbol is given by square of the distance between origin and the constellation point, right? So all the constellation points are at equidistant from the origin, right? So this distance, this distance, this distance, and this distance, all these distances are same, and the distance is square root 2, and its square of the distance is 2, right? So every symbol carries 2 units of energy, right? While if we compare 16 QAM, right? So if we compare 16 QAM, the energy, right? Energy for this symbol is different than this symbol, right? So only these four inner 4 points, inner 4 constellation points take the energy as the same energy as carried by the constellation points of 4QAM, right? So when we go for higher order modulation scheme, to keep the distance between two constellation points the same, right? So here also, see, if you see this distance, right, it is 2 units. Here also the distance is 2 units, right? So because it is 1, 0 and -1, right?
మేడం వస్తున్నారు మేడం వస్తున్నారా కాంటెస్ట్ అని చెప్పలేదు మేడం అదే మేడం మీరు వస్తున్నారు అందుకే ఫోన్ చేశాను మేడం ఓకే ఓకే మేడం ఓకే మేడం Okay, so in the meanwhile, till this speaker joins in, there are some instructions to be given to you. So tomorrow, the event, the second day of the event, will be ending at 8:30. This is only for the people who are attending for the ComSoc summer school. So tomorrow, the buses will leave the campus by 8:30, and only 6 buses are been arranged. The sheet is already been shared with you in the group. Again, I'm giving you the names of the routes. Number 1, Kugatpalli route. From college, it will start exactly at 8:30 p.m. in the evening. From college, Attapur, Madhipatnam, Panjagutta, SR Nagar, Kugatpalli, Y Junction, and Kugatpalli. I repeat again, the route for Kugatpalli from Vardhaman College, Attapur, Madhipatnam, Panjagutta, SR Nagar, Kugatpalli Crossroad, then Kugatpalli. The driver is Silo. Okay. Yeah, next one. The second route is Vanasthapuram route. Vanasthapuram. From college, Aramgar, Chandrangutta, OSC Hospital, Champapet, Bairamalguda, Sagar Crossroad, Astinapuram, BN Reddy Nagar, NGOs Colony, and Panama's Godown. I repeat again, for the Vanasthapuram route, from Vardhaman College, Aramgar, Chandrangutta, OSC Hospital, Champapet, Bairamalguda, Sagar Crossroad, Astinapuram, BN Reddy Nagar, NGOs Colony, Panama's Godown. The third route, Alwal route, for the Vanasthapuram driver, Malareddy. Then, the third one, Alwal route. For Alwal route, we have Parmesh. So from college, Afzalganj, Nagar, RTC Crossroad, Tarnaka, ECIL, Alwal. I repeat again, Alwal Road from Vardhaman College, Afzalganj, Nagar, RTC Crossroad, Tarnaka, ECIL, Alwal. Fourth road, Uppal Road. Uppal Road, B. Ravi. From Uppal, so from Vardhaman College, Balapur Crossroad, Gayatri Nagar.
use it. There is a link shared on to you. There is a link that has been given. This poster will be posted in your group. Yeah. In the WhatsApp group, we'll share you the document wherein you can just click the link and upload whatever the article you are trying to plan it. And it will be revised, or it will be evaluated by the expert committee of ComSoc people. All right? The link will be open till 9:30 tomorrow morning. 18 hours of time. Chalo.
Yeah. So tomorrow, so as we already shared you the complete instructions, tomorrow exactly by 9 o'clock, you should be in the auditorium. If you come within what you call by 9:05 or 9:10 also, we will close the door and you will not be allowed for the complete day. Okay? So thank you all of you. We'll see you tomorrow.